So next is Professor De Leon's second part of the lecture about measuring dynamics and correlations with quantum sensors.
Okay, is this thing back? Yeah, it's back on. Okay, so I think I only have like, I don't know, 10 minutes on the board, and then we can switch. I'll just tell you what my goal here is to get to the point where we understand how you use coherent superpositions and dynamical decoupling. I had an extra 3 or 4 pages of lectures on the actual formal kind of derivations of covariance sensing, but I think that might be like a little bit too in the weeds. So I don't know. Are they sharing lecture notes for this summer school? Do you guys have a drop? Okay, so you guys won't actually see these. Well, let me tell you, if you are really interested, step one, honestly, is just go to the supplement of Jared's paper because it's very nicely written out there and he's a very good writer. But if you really want my lecture notes, I can scan them and email them. So just send me an email and I will send them out. Okay, so right before the break, we talked about how you could do a T1 measurement where you prepare your population one eigenstate and then just watch it decay. And then now this population is going to decay as something that just looks exponential, e to the minus t over t1. So what I'm really measuring is this decay constant time. And then here, what we were able to do was connect this decay constant time to things that look like AC response in some material of interest. However, the key thing is that this really only works at the transition frequency, right? So I have this perpendicular magnetic field noise that's at omega naught. So if I happen to have some part of the spectral content that's at 2.88 gigahertz, that is great, but many things are not. Many things that are of interest are not. So what we want to do is construct a measurement where we can get access to a broader spectral range and can also sort of do spectroscopy and pick out what the actual spectral components are of this noise. So for noise far away, from this 2.88 gigahertz zero field splitting, in general, what we can do is measure the dephasing of a coherent superposition. And what this is called is we're going to measure T2 star, which is another quantity. And this is also called Ramsey spectroscopy. Atomic physicists call this Ramsey spectroscopy. NMR people just call it free induction decay. So on my block sphere, what this is going to look like. I've never really gotten good at circles on boards. Doug Osheroff can draw a perfect. Has anyone seen this? Like just a perfect, totally it's amazing. Okay. Okay, so what I'm going to do is prepare the superposition state. So this will be on the equator of the block sphere. And then after some instance of the experiment, this thing will, now we have to draw in 3D. So here's my equator. This thing will evolve so that when I do my final mapping of this phase onto a population, it will not all come back to the original eigenstate, right? So, and then if you have noise, there will be many different kind of places that I will land on this equator, depending on what the actual noise was over that particular free evolution time in the experiment. So what I will actually measure should look something like this. Let me just draw a pulse sequence to be really concrete because I think it helps. Okay, so what I have is my green initialization pulse that lasts about a microsecond. I turn on my microwaves to do a pi/2 pulse to go on the equator. And then I wait some time. And then I do another pi/2 pulse to map the phase back onto a population. Okay, and you can think of this however you want. You can turn it into a minus pi/2 pulse if you want, doesn't matter. And then what I will do is read out during this, this last green pulse. Okay? So remember, no photons while we're actually doing the phase evolution, only photons for initialization and readout. All right, so then what I should measure is that, again, all that I'm doing is counting photons at the end that are proportional to the final state population in ms equals 0. And what I should see is, you know, something that sort of oscillates with some envelope. And these coherent oscillations will decay as e to the minus t/t2 star to some stretched exponent factor. Okay. And the stretched exponent is going to depend on the exact characteristics of the noise that you're seeing. So if you had white noise, then this T2 star is going to look like non-unitary dynamics, and this n should just be 1. It will just be exponential, right? But if I had quasi-static noise, you can go through the math yourself, you would get an n equals 2. Okay, and then you can get weird stuff in between depending on what the actual characteristics of the noise are. Right. So generally in Ramsey spectroscopy, one way to think of it is let's ignore this envelope for a little while. And let's just say I have this coherent superposition. I'm letting this thing evolve coherently over time. And then my final readout is going to depend on this evolution over time in the magnetic field. And it should be roughly, you know, cosinusoidal, right? So if I look over time and I have this population, and then I think, okay, in one magnetic field, it looks like this. And then I change the magnetic field very slightly, and I do the measurement again. Let's say the magnetic field increases. Then these things are going to go a little bit faster. And what you can see is that the phase slips get worse as I go to longer times. So in general, the way that I'm going to construct my measurement is by sitting as far out on this curve as I possibly can, sitting at some slope, and then just looking at small excursions in the population around that point of highest slope. And that will give me the highest sensitivity to a magnetic field measurement that I can get, right? So I just want to let this thing run as long as humanly possible. And the thing that stops me from running super duper long is this decoherence time, right? So if I want to use this as a measurement of the static magnetic field, the game is get my T2 star as long as possible, which is isotopic purification, you know, stability of your magnetic fields, all of that stuff. But then the other thing that I can ask is, given that I have some background T2 star, I can now use this to measure noise, quasi-static noise of some system that I'm staring at, as long as that thing is dominant over my background T2 star. Okay, so generically, I want very long T2. All right, so that's where you're stuck if you want to look at DC fields. But we want to look at lots of stuff. So you can also ask about AC sensing and how to extend that to looking at noise across a broad range of frequencies. Okay, so sorry, let me just, to be absolutely explicit. So you use a Ramsey spectroscopy for quasi-static fields. So for higher frequency noise, what we need to do is a very similar measurement where we're looking at evolutions of this coherent superposition. But now what I'm going to do is extend past my bare T2 star by using dynamical decoupling. Okay. And this is why there's a star on T2 star, because you can sort of trivially extend your coherence by just driving the system. So the paradigmatic example is the Hahn echo sequence. For Erwin Hahn, so you know how old this is. Okay, so what I'm going to do is a pi over 2 pulse, pi pulse, and then a pi over 2 pulse. And these will have the same evolution times in between. Okay, and now what my block sphere will look like, well, here, let me do it this way. Yeah. I'm going to stop drawing the sphere if that's okay for everyone. Okay, so after my first pi over 2 pulse and my first evolution time, then what I now have is like, let's imagine I had 2 instances of this experiment where in one of them, my state vector ended up here, and in the other one, my state vector ended up here. Okay, so this is after some amount of tau, right? So I have some b times tau gives me that total phase. So now after this pi pulse, what I'm going to do is flip both of these things over some axis. I could flip them around here, but then it's hard for you to understand what's going on. So I'm just going to use this axis and then put them over here. Oh, I should have done this in different colors. I'm so dumb. The whole point of having this rainbow of chalk. Okay, so now I have these 2 guys with the exact same phase offset, but on the other side of the block sphere. But now this green thing was going this way around because of the noise that it was experiencing. So it's going to continue going in that direction. And the blue thing was going that way around, so it's going to continue going in that direction. So as I wait for tau, again, so as long as it's the exact same evolution time and they are experiencing the same noise, now these things will be both right at the same place in the block sphere. Okay, so I've canceled out all of my dephasing. So if I write that as up here, I'm going to write some relative phase, then I don't have any phase before I go on the equator, obviously. And then I start to accumulate phase that looks like b times tau. And then I do this pi pulse and I exactly cancel it out. And then in the end, modulo my bad artistic skills, these things should come back to 0. Okay, so the key is this allows you to cancel, in like NMR, what people use this for is you cancel out static inhomogeneity in your magnetic field because you're not that good at making a magnet that is perfectly homogeneous over your whole sample volume. And then one way to cancel out all of that inhomogeneity is just by doing a Hahn echo sequence. In our case, what we care about are quasi-static fluctuations in the magnetic field, which can arise from, for example, slowly fluctuating carbon-13 nuclei in the environment, right? So you have these very long T1 nuclear spin flips that sets your bare T2 star. Okay. More generally, Oh, and let me just mention, I wrote this down during the break, but a lot of this stuff is spelled out kind of nicely and explicitly, and with the connection drawn to condensed matter physics in this paper that's currently in review, that's up on the archive. So it's a review paper on NV sensing for condensed matter. So you can write down the archive number. Okay, so more generally, you can use lots of pi pulses to now cancel out even higher frequency noise. So here, the only thing that this was good at was something that gives you the same phase evolution in this block as this block. So it's quasi-static noise over the length of the time evolution. So more generically, if I do something called, for example, all of these pulse sequences are named after, like, for some reason, 2 to 5 people. So you just get these very, very long kind of acronyms. So CPMG is Carr, Purcell, Myboom, Gill, I think. But they get weird. There's one that's called like Wahooha. Anyway, there's a lot of pulse sequences that cancel out different dynamics. But what this looks like is I just have a bunch. Those should be closer spaced together than farther. Okay. I have a pi over 2 pulse here, pi over 2 pulse here, pi, 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 pi. And then you can just, put as many of these as you want in there. And the evolution time here is all tau. And then at the ends, it's tau over 2. So now I guess there are 2 pieces of this. One is that this allows me to extend my coherence time longer because now I can cancel out higher frequency noise, right? The threshold is no longer is something quasi-static for this entire time evolution, but it's really just the time evolution in one of these blocks. So as I fit more and more pulses into the same total time evolution, I cancel out higher and higher frequency noise. But the other thing that's kind of interesting is I can use this as a tool for getting enhanced sensitivity to noise that just happens to be at a frequency that's commensurate with the pulse sequence that I'm using. So if you imagine that I have some AC magnetic field that is exactly coherent, if I can draw it that way. Let's see, okay, I need all of my flips to be at the flips, so. Ugh. All right, I don't know if that actually worked, but then what you have is that the sign of the magnetic field flips when the phase evolution of the NV center flips too. So now I accumulate phase here. I also accumulate the same amount of phase here. I accumulate the same amount of phase in this block and this block. So now instead of having this phi go up and down and cancel, what I actually have, and I never have enough space to actually do this, is something that looks like we're up in this block, and then up further in this block, and then up further in this block, and up further in this block. Okay. So now for noise that happens to be at very specific pathological frequencies compared to the sequence that I apply, I can actually accumulate lots of phase. So now I am maximally sensitive to this kind of stuff, minimally sensitive to everything else. So the way that you can think of this is as a filter problem. Sort of an analogy to designing bandpass filters and things like that in electronics. And there was seminal work by Lorenzo Viola and Seth Lloyd in the late 90s, basically formalizing exactly how you think about these dynamical decoupling sequences as a filter function. All right, so the very last thing that I want to say is that, in general, what you're going to measure is, again, some coherence decay. Which is going to look like, T over T2, again, to some stretch exponent. And now if I have some dynamical decoupling sequence, with some total time t, which is going to be, I'm going to use big N for the number of pulses, times my phase evolution time, then my T2 that I measure is going to look like gamma squared over pi t to the n. And what I'm going to integrate over is now a different part of the spectral noise density, which is the perpendicular, which is the parallel component. So here, I'm not trying to get non-unitary dynamics by flipping the spin. Here, what I'm looking for are small changes in the Hamiltonian, right? So changes in the energy at the zero field splitting that then manifest as phase evolution changes on the equator of the Bloch sphere. And then what this is going to look like is basically the spectral noise density times some filter function that is related to my dynamical decoupling pulse sequence. So now I can pick my pulse sequence to choose which noise that I want to look at. So for CPM, oh, sorry, I didn't need to do that. For CPMG, this filter function looks like this. Something messy with a lot of high powers of sines and cosines. It doesn't really matter what it looks like. I think it's pretty clear that this is going to be very sharply peaked around some omega that looks like pi over tau. Okay, so loosely speaking, I put in a whole bunch of pulses, I pick a window, and then that's how I'm going to do these measurements. Okay, so I will stop there with the board, and then we can switch to slides, but if there are any questions, we're going to cover up the board so you can't ask. Yeah, go ahead.
I understand the passing. You just say on echo sequence is supposed to know, like it'll cancel out.
Yeah, so
Like it cancels out everything. What's it actually?
No, the Hahn echo sequence will only cancel out field noise that is quasi-static. So you leave behind everything else. So the other way to see it is like the Hahn echo also just has some filter function. It's just a very broad, sloppy filter function.
But if you have like a clean sinusoid, that would be, so monochromatic noise, not a noise map.
Yeah, it's just a coherent measurement.
Right? So as long as you're going to get, you want this power on small enough that you're run this experiment at the time, and you're going to get some very.
Yes, what this will allow you to do is get a more sensitive measurement of the magnetic field than you would have with just Ramsey, because now you've canceled out all your nuclear spin noise, and then I can evolve phase for longer and then push down the sensitivity. So when I quoted this like nanotesla per root hertz earlier, that's really the Hahn echo sensitivity. I think the DC sensitivity is closer to like microtesla per root hertz. Yeah.
So when quantum computing people talk about the coherence times of their qubits, do they talk about the T1 or T2?
They're talking about T2. And specifically, depending on the exact kind of qubit, they're talking about T2 and not T2 star. Because oftentimes, when you're doing gates on these, well, okay, people can get into fistfights. when you're doing gates, that's a little bit like dynamical decoupling, right? Because you're already driving your qubits pretty hard all the time. So what you can do is design your gates so that they are useful dynamical decoupling sequences. And then you can take advantage of, longer lived coherences, basically. So a lot of modern processors are built on quite a bit of dynamical decoupling.
So that's like putting error correction in the actual computational gates that you want to do.
So it's not error correction because it is not removing entropy in any meaningful way, but it is, I don't want to use the IBM propaganda, error mitigation, but it's, it's something like that, where you're sort of defining the problem in a way where you can take advantage of longer coherence. You get rid of all of the quasi-static problems. Okay, so hopefully everyone is now an expert on how to use NV centers to measure stuff. So let me just tell you a more recent story about stuff that's happening in my lab, how to try to connect these things more strongly to condensed matter systems. So you guys already know all this, so we can skip it. So what most people in NV land use NV centers for is, again, this nanoscale sensing. So the idea is, let me take my NV center and look at, for example, just dipolar coupling to other things and draw contours of equal strength. It's sort of obvious that you're going to get these contours changing over very, very tiny length scales. So in a sense, this looks a lot like magnetic resonance imaging, where you have these very, very large magnetic field gradients, and then you can use that to do, some sort of spin measurement of the outside world. But now I have the largest possible magnetic field gradient because I have this true point sensor. So there's a lot of people who are doing that, including my lab. So, taking biomolecules, sticking it on the surface to try to do nano MRI, taking very small volumes of liquid and doing nano NMR. But then I think the other kind of giant community in NV sensing is really focused on condensed matter applications because it's, a really new probe for being able to do magnetic field sensing in all of these materials. So this is a particularly nice example that's now, oh gosh, 5 years old, from Patrick Malatinsky's lab. They were looking at chromium triiodide and using a scanning NV center to look at magnetic ordering. I guess there was some puzzle in the field about why you had such a large net magnetic moment when all of the layers were antiferromagnetically coupled to each other. And what they were able to find was sort of definitively show this even-odd ordering of the magnetization, and then showed that if you made a defect, that you got kind of very weird magnetization around the defect, and that sort of, explained this puzzle in the bulk. Okay, so this sort of goes to what we were discussing earlier, which is, then you can ask, all right, these NV centers seem really nice, but you have to actually put numbers to what you can see and what are the nice frequency ranges and sensitivities. Okay, so this is our attempt to try to put this in context of other probes. It's not exactly fair because not all probes are quantitative. So it's not like a lot of times you're just looking at some response that you don't really understand, and then you're looking at relative changes. So there isn't like a neat sensitivity calculation that we can write down for things like optical measurements or neutron scattering, but we just tried to indicate the length scales and frequency scales here. So as I mentioned earlier, NV centers really get you down to this nanometer length scale, but not meaningfully the angstrom length scale. So they're sort of a complementary tool to the kinds of things that you can measure at very high K, basically, with neutron scattering. And then kind of the happy frequency range for this very high sensitivity sensing is something like kilohertz out to, let's say, 100 megahertz. And what that is set by is, remember that our ability to measure sort of arbitrary magnetic fields comes from these pulse sequences. And the question is, how fast can you drive your NV center? So what you need is a very, very high oscillating magnetic field at the NV. You probably have to be inside the near field of some antenna. And then you also have to generate these pulses, and you have to generate them coherently. So in general terms, the speed limit to that is like 10 nanoseconds. It's going to be hard to do a lot faster. And then, of course, there's this T1 sensing that we can do at the NV resonance frequency. But we can move that NV resonance frequency around with a bias field, right? So we're not stuck at 2.88 gigahertz. You can kind of go a little bit farther. There's also some more modern techniques with frequency mixing that are very nice and clever that sort of extend this range a little bit. So you can see if you look at the color bars, you're sort of competitive with scanning squids. You have a lot of this range that's similar, but the difference is that we can get to much, much shorter length scales because squids are, kind of large objects. But then more importantly, there's nothing that we can put for like MFM and squids that's out here, because those are really DC measurements. And even when you're doing lock-in, that's DC, right? So there's no way to get to these kind of 100 kilohertz, megahertz frequency scales. So I think this is this review paper that I mentioned earlier. We sort of worked pretty hard with Saranko Palakrishnan and Eugene Demler to like sit down and say, what do people actually need? What do people actually need, and what are the relevant scales? Okay, so so the way that most of the field thinks about how you probe condensed matter phenomena are really just these two modes that I told you about. So one is you just measure the magnetic field, right? So you can do a static measurement, and for example, you can run current in a device. This is you know, some nanofabricated sheet of graphene. This was from Amira Kobi and Ron Walsworth's groups a couple of years ago. And what they did was just use the NV center to look at you know, magnetic fields arising from this driven current. So they just drive a current, and then they map where the current is by doing magnetometry. This was from Anya Jaich's group, where they were looking at pinned vortices in some high TC superconductor. So you know, you can do stuff like that. And then you could also do noise measurements. So this was an example from Misha Lukin's group a few years ago, where they also were looking at graphene. They stuck graphene on top of a diamond and then looked at T1 of these NV centers as a function of position as they drove this current. And then what you saw was this sort of surprising explosion of noise near the contacts that they attributed to some some exotic electron photon scattering thing. And that's essentially the entire field. Is, you know, either you do this or you do this, and that's kind of what you're stuck with. I mean, this is pretty nice because this is something you can't do with other probes. So what we became interested in was, all right, condensed matter theorists do not sit around calculating what magnetic field you get at some offset distance away from the material. What they do is they sit down and think about susceptibility, dispersion, transport. They really like order parameters, and they really love correlation functions. So one question was, can we develop a sensing modality that more directly connects to some of these sort of parameters of interest so that we can directly compare to theory? And to motivate this, you know, measuring these correlation functions a little bit more concretely, for example, if you imagine that I'm looking at these red dots here are my NV centers, and I have a whole bunch of them, and I can pick which ones I'm looking at. If I'm looking at Johnson noise from some, you know, material that's sitting on top of it, then you can imagine that if you have ballistic transport that has some characteristic length scale lambda, then two NV centers here are going to see highly correlated Johnson noise because they really come from transits of the same electron that's going past them, right? Whereas if I pick two NV centers that are really far apart from each other, they will not see correlated noise. So now by looking at these correlations, I actually get access to a new parameter that I wouldn't have been able to see with just noise sensing. Because if I asked all of these NV centers, what noise do you see? They would have each reported something just really boring and trivial. They would say, I see Johnson noise. So I see a white spectrum, and that's it. But now by being able to look at these correlations, I can actually get out something about the spatial structure factor of the transport that would have been hidden otherwise. This is kind of a nice proposal from Eugene Demler's group, where they're thinking about the BKT transition in thin film superconductors, where you get these vortex-anti-vortex pairs. And as you go through the phase transition, the correlation length scales between these vortex-anti-vortex pairs kind of explode. And then you eventually, you know, break symmetry and get sort of these unidirectional vortices. So one question is, you know, it's actually very hard to see these vortex-anti-vortex pairs, and this is a very dynamic system. These things are moving around like crazy. So any of these static probes are not really going to catch them. But maybe if you are looking at NV centers, what you should be able to see is this pretty big anti-correlation signal that's at some characteristic length scale. And then I should be able to go through the phase transition and see the signal kind of explode. Okay, so let me tell you two quick stories about ways to access these correlation times and correlation length scales. So this is a weird correlation time story. I have no idea how this is going to go, but we're going to try it. So we started thinking about what you're actually doing when you do these coherence decay measurements in the context of kind of a weird system. So we have these pathological surface spins that just exist at the surface of diamond because you have dangling bonds and things like that. And everybody sees them. And actually, we don't because we make good diamonds, but we can make slightly less good diamonds and then see these things. And what you can see is, you know, I take an NV center, I do something called a double electron resonance measurement, which means that I do this Hahn echo, And then in the middle of my Hahn echo, I have another microwave tone that drives these surface spins spectroscopically, individually. So the idea is this is a totally different microwave tone. It's relatively narrow band. So that means that I'm only driving these surface spins and nothing else. So my Hahn echo does a good job of canceling out all my quasi-static noise. But because I flipped my surface spins at the same time that I flipped the NV center, I pathologically pick up noise from the surface spins. And that gives you a measurement of my coupling to the surface spins. So if I do one of these Deer measurements, I start with this bare Hahn echo decay. And then I do this Deer echo sequence. And you can see that my coherence is suppressed. So I can just take the ratio of these two curves, and then that gives me my Deer coupling. And then now, this is formally the same thing as doing a free induction decay measurement on the surface spins. And I can ask, what is this coupling to the Deer spins as a function of distance away from the surface? And you see that there's this kind of nice dependence, whereas you get closer to the surface, you see greater coupling. So that sort of proves that they're all sitting at the surface. So what we were playing around with were methods to try to get rid of these surface spins and decrease their density. We have a whole bunch of surface spectroscopy we do, it doesn't matter, but we can get rid of this dangling Bond peak, and that corresponds to sort of suppressing these surface spin densities. Well, it doesn't matter what the puzzle was, but we had this long-standing puzzle in the field that none of these numbers actually made sense. And the resolution to the puzzle, I'm just going to give away the story right now, is that these surface spins can hop around and reconfigure. And once you put in configurational averaging, it all works out nicely. But so that gives you these kind of nice scalings with distance that all are sort of rational. Okay, so the thing that we realized, actually it was like during COVID. So we had like sat down and couldn't be in lab, so we were just staring at data. And there was this thing that a bunch of people had gotten yelled at in my group over the years, which was that they would come in with this Deer measurement, and then they would fit their coherence decay, and they would say, okay, so this goes as e to the minus gamma tau to the 0.5 or something crazy. And I would say, like, that's literally not possible. So you must be analyzing your data wrong, undergrad, and go back and constrain the data so that it fits to 2, because I know that it should be 2. And the reason that I know that it should be 2 is that for free induction decay measurements, the stretch exponent should always be 2 in the quasi-static limit. It's like 2 lines of math. In pathological cases, you can get this n to be 1 if things are really crazy, but it didn't seem like the n could be 1 because we see, we actually see these things somewhat coherently. But you can only go down to 1. But if you take a careful look at this data and you oversample like crazy, what we found was that actually quite a few of them had an n less than 1. And there's just nothing that I can write down in like Abraham and Bellini that actually gives me a stretch exponent that's less than 1. So this just seemed like a weird puzzle. I apologize retroactively to all of those undergrads. But then finally in COVID, we like sat down, analyzed the data carefully, talked to Misha's group and said, are you guys seeing the same thing? And then kind of put our data sets together. Okay, so what we see is, again, the puzzle here is we see a bunch of exponents less than 1, and we see like sort of a depth dependence, that as you get farther away, you get exponents that creep up towards this 2 value that you would expect. All right, so the analytics here are that what I showed you earlier, where we just say the coherence decay goes as e to the t over t2 to the n, and this n is always 2 or 1, and then you get this phenomenological parameter that can change depending on the type of noise that you have, is just like fundamentally incorrect. So this is what we always teach our grad students. But n equals 2 is correct. That is a correct result. N equals 1 is also correct. But anything in between actually is not just a single exponent for the entirety of the phase evolution. So, okay, what do I mean by that? So what I mean is that for any given noise bath, what you actually have is a characteristic crossover time, where at very short times, what you have to see is quasi-static noise, because you're far enough away from whatever it is that you're looking at that instantaneously everything looks like quasi-static noise. Basically, you're outside of the bandwidth of the noise bath. So what you should always see at very short times is n equals 2. And then as you start to hit the correlation time of your noise bath, this n should just change. And this change is relatively sharp. because what you're doing is crossing over this boundary of the spectral noise density of the noise. And then what this should go to is something that gives you some characteristic shape of the noise. So generically, for most things, what you should see is n equals 2 to n equals 1. In this case, because we're looking at surface spins, what you get is an exponent that looks like the dimensionality of the bath divided by the strength of the interaction. So we get 2/3 because it's dipolar interactions. So this is the prediction that what I should see if I just oversample the heck out of this coherence decay and then plot it on a log plot. So what I'm doing is now the slope of this thing is just this stretched exponent. I should see a transition from n equals 2 to n equals 2/3. And then because this transition depends on when I have dipolar coupling with my surface spins, I should see this transition at later and later times as I move my NV center far away from this surface. Okay, so yes. No, it's I have a single NV center, and then I'm just asking where do I see this critical crossover time from? It's still this Deer measurement, so I'm still looking at the free induction decay due to dipolar coupling from these surface spins. Okay, so there's kind of a nice geometric picture, which is that at short times, you can sort of think of the time as giving you some total volume where I could have strongly coupled to the first surface spin. And there's some short time where this volume just has, the sphere has not intersected the surface yet. So everything looks like quasi-static noise. But then now, once I hit the surface, I should start to see this area law scaling, and that gives me this n of 2/3. All right. So then, armed with that theoretical explanation, or this theoretical model, what we can do is now intentionally oversample the crap out of a bunch of coherence decay curves, and we see this actually pretty nicely. So we see this crossover time. We can independently measure the distance from the surface by doing proton NMR. So we basically just do one of these coherence decay measurements, look for a little peak in the noise that comes from the Larmor precession of protons at the surface. So we just put oil, and it doesn't really matter. But anyway, so we get out these independently measured depths, and it actually matches where this critical crossover time should be just based on the distance very well. Okay, so the cool thing here is that you can measure something about the dynamics of the system and the correlation times of the system, and you can kind of pick how you measure it based on placing your NV center in different places. But let me just say, more generally, I can always use this trick to measure the correlation time of the noise and the spectral noise density in a very easy way, because this is just a Hahn echo, right? So we have some recent collaborative work with Abe Pasupati's group, led by his group, Mark Ziffer, who's I think like research scientist or something, in his group with Jim Shuck and others over at Columbia. And what they were looking at was the very confusingly named CRISPR, but it's this chromium sulfur bromide 2D magnet. And the really interesting thing is, okay, you can use these NV centers to just do stray field mapping, which is what most people do. And if you do stray field mapping and you go over this nail temperature, you have this pretty messy, like big, broad thing that's actually pretty hard to disentangle. And you can't really see the nail temperature very cleanly. But then if I do one of these measurements where I just look at the critical correlation time by oversampling the decay, and I just plot 1 over that time as a function of temperature, you can see this really clear peak that comes from fluctuations in the magnetism. So here, by looking at noise and then asking what is the spectrum of that noise in a relatively easy measurement, I can see the nail temperature very, very well. And you can imagine if there's any heterogeneity, I can now start to do this in some site-resolved way where I can do these local dynamics measurements. Okay, so that's just correlation time. Now let me get into these spatial covariance measurements. So this is another modality that we've been playing around recently in the lab. All of this work was led by Jared Rofny, who's a postdoc in the group, and we've been working in close collaboration with Shimon Kolkowitz, who's over at UC Berkeley. So the setup is, I just have, instead of just measuring one NV center, what if I just measure 2 NV centers? and then try to look at the outcomes of their measurements simultaneously over time, and then compute correlations between these measurement outcomes. So the setup is, each of these NV centers is looking at some correlated noise that comes from, for some reason, we always draw silver, but some sort of material that I'm interested in. And then, of course, they're each going to have some uncorrelated noise that I don't have any control over, like nuclear spins or something like that that are not shared between the NV centers. So what I'm going to do is a Ramsey on both of them. So I take both of my NV centers, prepare them on the equator of the Bloch sphere, let them accumulate phase, map that phase onto a population. And then now, remember, when I get my population, I'm just writing down the number of photons that I got in that shot. Okay, and then I can stick whatever I want inside this Ramsey. So we talked about CPMG. You could do XY8, whatever it is that you want. And then use that to do some spectroscopy of this noise. And then all that I'm going to do is take my two NV centers and then write down these measurements as a function of experiment, and then just compute a classical correlation between these two traces at the end. That's it. Super easy. Super duper easy. So why hadn't anyone done this or even thought that this was possible? So this works out very trivially in the case that you have a perfect readout. So if I have absolutely no noise on the measurement, then this is really easy to do. The hard thing is that now what I care about is, I have some total signals that I've measured at the end as a function of the underlying correlation in the phase. But what stands in between me and that phase distribution is quantum projection noise, which says that I am not going to actually do this phase to population mapping perfectly, right? There's always going to be some quantum noise on that step. And then second, I have readout noise, which says that I don't even measure these populations very well, right? So remember that I gave you this back of the envelope, that I get 100 kilocounts per second. My readout window is only 300 nanoseconds, so I only get 0.03 photons per shot. So that means most of the time I'm actually measuring nothing, right? Most of the time I'm sitting in the dark. And the only reason that we're able to do all of these beautiful magnetometry experiments is that I have a rep rate of like 1 every 3 microseconds or something, so I can just average like crazy. Yeah. Yeah, let's talk about that at the end. Okay, so here's the way to see it, is that conventionally, most of the time I get no photons, and every once in a while I get a little blip. If I'm trying to measure this covariance, it's the same thing as sort of seeing a coincidence between two NV centers, and the probability of seeing a coincidence is very, very low, so I'd have to wait forever. So it turns out that there are other readout schemes. This is something that I helped develop when I was a postdoc in Misha's group. What you do is just convert the spin to a charge state selectively, and then the charge state is very easy to read out, because once you map the spin to a charge, the charge states just have totally different fluorescent spectra, so it's very easy to distinguish NV0 from NV minus. We can get single shot readout of the charge state very easily with extremely high fidelity, like 99%, essentially unity fidelity. The main reason that nobody uses this, we were very excited in 2015, and then we're immediately not excited, is that the overhead for doing single shot charge readout is a millisecond. So if you were doing conventional magnetometry, you would rather just do your measurement screaming fast, right? And average like crazy every microsecond rather than taking all of this overhead. So the reason that this now makes sense is that we really care about readout fidelity. We care about readout fidelity squared. And then now we're willing to take this hit to be able to measure this correlation function. So here's how you actually want to parameterize it. You want to write down a sensitivity curve that says what is kind of the minimum noise amplitude that I can see in this correlation as a function of experiment time. So if I had optimal readout, I would have a curve that looks like this. So to get to about a nanotesla, I would need to average for like a minute. Which is not a fun experiment. A minute is long if you think that that's your rep rate. But there's no other way to measure these correlations, so we're not really competing with anything. But that's optimal readout. If we did our conventional readout, which is the thing that I outlined for you on the board earlier, that's at 35 times the quantum projection noise limit. So this would now take 1 million seconds, which is an unacceptable fraction of a PhD. So we can't do that. So this spin to charge conversion gets us a little way back where these measurements now take like 1,000 seconds, which is I just, full disclosure, very painful. This is like not a fun experiment to do. But again, the only way to get these 2-point correlators. So still worthwhile. Okay, so that's a theory. It seems like we should be able to measure these correlations. We set out to experimentally implement it, which is pretty straightforward. We build one of these microscopes, and then instead of just building one channel, we build 2 channels. So we have 2 separate channels that we can use to point at 2 separate NV centers. And then we have to implement the spin to charge readout. The thing that we discovered essentially right away is that the big experimental challenge is that when you go to make a machine that measures correlations, everything has correlations. There are a lot of very trivial correlations. If I take my optical table and do this, that also gives me a correlated fluctuation in the photon counts. And you can see that if you just take your data and do a point shift, then for something where you shouldn't see any correlations, this should just go away. But if it's some coherent noise essentially on your table, then it will show up as this. So few months, an enormous amount of pain, lots of MacGyvering later. I'm very confident now have the world's quietest single NV experiment by a lot, because it's really hard to do this 2 NV stuff. But it is doable. So here's what it looks like. So this is a scanning confocal image. Each of these little bright dots here is a single NV center. Super easy to see. And then what we're going to do is pick 2 of them out, and then now just do this Ramsey on both of them, and then plot joint statistics where I ask if my first NV center is dark, is the other one dark? If my first NV center is bright, is the other one bright? And I'm going to get a bunch of checkerboard patterns. So my background correlation doesn't show anything. And then what I do is I turn on some 2 megahertz noise tone that comes from some antenna that's nearby. And then what you see is this is data. This beautiful checkerboard pattern that emerges that shows that these 2 things are nicely correlated. And then now, because these things are qubits, I don't have to prepare them on the same side of the Bloch sphere. I can do whatever the heck I want with them. So now I can prepare them on antipodes of the Bloch sphere. And what you should see is that this correlation should flip to an anti-correlation. And this is a very nice kind of internal calibration sanity check that if you're really looking at spin-spin correlations, you should always see something that just flips when you actually flip the spins. So we can also put whatever we want in here and do spectroscopy. So now I can use an XY8 sequence with some narrow filter function and scan this over this 2 megahertz signal. And then what I see is, remember, this is sharply peaked at omega over tau, or at tau is pi over omega. So what I see is some sharp peak that corresponds to my 2 megahertz signal. And then when I do this antipode measurement, it flips to an anti-correlation. That's a nice mirror image. Okay. So I can see correlations in the noise. I can do spectroscopy on those correlations. What can I do with this? The first is that I can start to now disentangle the spatial structure factor of different sources of noise in the material that I'm staring at. So generically, if I was just doing sort of single NV noise detection, then what I would do is a coherence measurement, and then maybe there's some narrow band noise sources that give rise to these little dips in coherence. And then I can just translate that into some spectral noise density, right? So I have 2 peaks in the noise. But now, these are just, all of my NV centers will report the same thing. I just see these 2 sources of noise. So now if I do this covariance detection, maybe only one of them pops up, because that's the shared noise that actually comes from the material. And then there's a whole bunch of other stuff that's uncorrelated. So now what I can do is combine these 2 measurements and then label one of these peaks as the correlated peak and then the other peak as uncorrelated. And I can, go back here and just pick different inter-NV distances to map out what these correlation length scales are. All right, so this is that measurement. So we have 2 NV centers. The single NV noise spectral density looks like this. This peak turns out to be some weird harmonic of the nitrogen nuclear Larmor frequency. So that is not shared. That is some local noise. So when we look in covariance, only one of the peaks pops up. Okay, so we can label them. There's also kind of an interesting, this is more interesting to metrology people, maybe not condensed matter people, scenario that arises if I have perfectly correlated white noise. So now I just turn up, the noise on this antenna a lot so that the NV centers totally decohere if I look shot to shot. So I've turned the coherence down, the coherence time down to like hundreds of nanoseconds. Normally, you wouldn't be able to get any information out here where the NV centers are fully decohered, right? It's just noise. But because this is correlated white noise, it means that in any given iteration of the experiment, they are landing at a random point in the Bloch sphere, but they are always landing at the same random part of the Bloch sphere. So if I look at these two NV centers, they should be moving around together. So if I look in covariance, I can cancel out this common mode noise and then now still do spectroscopy. So this is now nuclear spin NMR way out here in the tail of this shared noise. This is a trick that like atomic clock people use all the time because they're mostly looking at global noise that comes from phase noise in their lasers. So if you can do differential measurements to look at these correlations, you can get a better measurement. All right, there's one last trick, which is that, again, because these NV centers are qubits, I actually have quite a bit of control. So if I can pick two NV centers that have different magnetic resonance frequencies, in this case, they're just different orientations with respect to the magnetic field, then I can use independent microwave control to change the timing of the sequence. So what I can do is start the clock on the first NV center, wait some very short time delay, and then start the clock on the second NV center. And now what this gives me is a probe of not only these correlation functions, but the temporal dynamics of the correlation function. So this is a measurement of a phase random signal. So shot to shot, the phase is completely different. Like I already said, these measurements take many, many hours. So there's no way to make a microwave tone that has coherence times of many hours. But because I'm looking in the stroboscopic relative phase accumulation mode, I recover sort of the coherent oscillations in this phase random signal. All right, and then I can do the anti-correlation stuff. And if I just turn down the coherence time on this phase random signal, you can see that I can look at dynamics that are very short compared to things like the spin polarization time. Right, so normally the overhead of these NV center experiments would be how long does it take me to polarize and read out the spin, which is a couple microseconds. But here I can look at dynamics on much shorter timescales all the way out to the Rabi frequency, basically. So my speed limit is just how fast can I do this pi/2 pulse here. Okay, so just to summarize, what the technique does is it gives us access to this 2-point correlator in the magnetic field. So anything that looks like BR1T1, BR2T2 at what I've shown you so far is a few hundred nanometer to a few hundred micron length scales. So everything has so far been diffraction limited, but let me show you something else that's new. And the thing that's really exciting about this is, as far as I know, this is essentially just not physically accessible with any other technique. Neutron scattering measures correlation functions, but not in real space, and you're averaging over some fairly large bulk sample. I guess you can kind of do weird things with like optical pump probe, but again, those are weird things. So not exactly sure how to compare. So I think this is a very exciting new tool that gives us, a completely different handle on trying to understand some of these material systems. Okay. So let me tell you about what we have been doing since we published that paper. So the first is that, what I showed you so far is that you pick two NV centers that you can resolve optically. I collect the statistics from each one of them, and then I compute this correlation at the end. That forces me to work beyond the optical diffraction limit. And lambda/2 in this range is like 300 nanometers. There's a lot of condensed matter physics that happens below 300 nanometers, as you know. So what we would really like to do is come up with a way to measure these correlation functions far below the diffraction limit. So in principle, there's actually nothing that stops me from doing this. So if I, for example, pick out this bright spot here, there's two NV centers that are separated below the diffraction limit. And then what I'm going to do is just measure their joint statistics, right? So if these guys are correlated, then what they should show up as both bright or both dark, and then sort of nothing in between. If they're anti-correlated, then I should have a sharply peaked distribution because they're always bright, dark, dark, bright, right? And I don't care which one is which. All that I care about is kind of the moments of this distribution. And if they're uncorrelated, then I get some average over those two distributions. So this is exaggerated. You don't actually get this because our readout noise isn't this good. But in principle, this shows you that just by characterizing the variance of this joint distribution, I should be able to make some statements, some quantitative statements about the covariance. The reason that this turns out to actually be like really hard is that if all that you're looking at is the variance, and I have thrown out all of the individual statistics information that I have, now anything that gives rise to small mean value fluctuations will mask as a variance. And it's actually very hard to tell if I'm looking at technical noise or actual correlation functions. So what you need is some way to be able to do, to construct the measurement so that you can compare and then cancel out these mean value fluctuations. And the trick that Jared came up with is actually an old trick from NMR called phase cycling. So the idea is that you just construct your experiment so that at different iterations of the experiment, you land at different places in the block sphere. So you get an overhead of like, you now have to do 4 different pulse sequences instead of just one. And then if you just write down math between all of the sequences, they should all cancel. All of the mean value fluctuations should cancel, and what remains is the covariance, as long as everything is good. So basically what we use is NMR phase cycling as a reporter on these mean value fluctuations, and that allows us to now get this covariance at length scales far below the diffraction limit. Okay, and then the idea is, so now I have these joint statistics. Let me just skip ahead for a second. What I can now do is combine this with this giant suite of super resolution techniques that people have made over the last, I don't know, 2 decades now. Storm, POM, STED, Resolved, I think you know all of these like acronyms. And the kind of neat thing is that for NV centers, actually, who's familiar with these super resolution techniques? Should I do? Oh, almost nobody. Okay, so let me just explain the principle because it's super easy. So the diffraction limit just tells me that if I have 2 things that are really close together, I can't focus light down below some limit. So I'm always going to be collecting their joint statistics. But if I have one of them turned off, and then I collect photons from the other one, then I can fit the centroid of that position with much greater precision than the diffraction limit. Right? I can just keep on collecting photons and fit the centroid. So if I have a way of turning this guy off, fitting the centroid, and then flipping, turning this guy off and then leaving this one on and fitting the centroid, I can actually get information about the positions of these emitters all the way down to like, I think there was a Nature paper last year that claimed angstrom length scale. Whether or not that's really possible, I don't know. But nanometers is easy. For NV centers, this is trivial because we have coherent spin control and then spin to charge and PL-based spin readout. So I can just turn them off and turn them on at will and then figure out where they are. So these 2 NV centers are, I don't know, 50 nanometers apart or 100 nanometers apart or something, and we can figure out where they are and we can do these joint statistics. Yes. Yes. So these are still different microwave frequencies. So what we've done is picked a pair that is close enough together with different orientations so that we can select them independently. Now that's actually like not a good statistical cut on your total data set because it means that a lot of the pairs you can't use if they happen to be the same orientation. So we have another trick that I'm really excited about, which is that you can use the fact that the local environment of these NV centers is a little bit different, and that local environment can actually involve qubits. So here, what we have is 2 NV centers. You have stochastic population of carbon-13 nuclei nearby. These carbon-13 nuclei are extremely coherent, so they're actually very good qubits. And you can do this weird thing that's kind of like a 2-qubit gate, but it's like, well, it's not a C0. It's like a C, is there a carbon-13 or something? But basically, so what you see is if I do XY8 on these NV centers to do spectroscopy, there's this big C13 bath. And then I can find a coherently coupled C13. And what that means is that I can derive gates with XY8 that only select for this NV center and not the other NV center because it has this carbon-13 handle. So now all that I need to do is independent microwave control to do this phase cycling. So this now carbon-13 handle is something that we can also use to get covariance measurements below the diffraction limit. I think I don't know if you guys care, but NV people love this stuff. Okay. The last thing that we can do, which was a question in the back, is if these NV centers are close enough together so that they have dipolar coupling with each other that is faster than their bare decoherence rate, I can actually just use Bell states, right? So I can entangle the two NV centers and then use their Bell pairs as another basis for sensing. So this is now two NV centers that are like 10 nanometers apart from each other. So they have, I don't know, 150 kilohertz dipolar coupling. I can see this NV Deer coupling very nicely. It's exactly the same Deer sequence that I showed you earlier, where the second tone is now on the other NV center. And then now I can just prepare two sets of Bell states. And the antisymmetric Bell states are in a decoherence-free subspace, which means that any noise that is shared between the two NV centers should not be seen by these two Bell states. So now all that I have to do is a differential measurement where I make one of these Bell states and one of these Bell states. So this is like the tiniest GHZ state or something. And then I just look at the difference in the outcomes between them, and then that reports on the covariance. Okay. And interestingly, actual entanglement enhanced sensing, because now what we have is a phase that evolves, a factor of 2 faster because of these Bell pairs, which means that I can do √2 better in my sensitivity, and I have paid no penalty because this was like actually pretty easy to do. All that I needed were 2 NV centers that were close enough apart. This is by far, given that I have 2 NV centers that are 10 nanometers apart, this is by far the easiest experiment to do. Yes. Yes. Yeah, so we still need some kind of independent microwave control so that we can prepare them. But I've already shown you 2 ways that we can do that.
Work again for like a Bell test, you kind of like adjust the polarization angle and you make like, I don't know, 8 or 16 different measurements, right, at relative angles. But isn't it fixed by the quantization axis? So like which sublattice your NV sites sit on?
No, because all you have to do is adjust the phase between them, right? So you don't actually need, it's not that you have to prepare this, right? It's that you make your Bell state and then you let it evolve for some period of time, and then you measure it. You measure where it ended up. Okay. The other kind of interesting opportunity is that these single NV measurements are extraordinarily slow, which just sucks. It's really bad. It also makes like scanning really hard because then you're sitting there collecting photons forever, and then you move half an angstrom and then do it again. So like your one figure in the Nature paper takes, I don't know, a month or something. So one thing that's nice about this covariance stuff is we're just computing a correlation at the end, right? Which is very easy because all I have to do is write down my arrays of numbers, and then I just do this calculation. So nothing actually stops me from taking measurements on 10, 100, maybe even 1,000 NV centers simultaneously, and then just computing all of the pairwise correlations at the end. The thing that stops me is that as recently as like 4 or 5 years ago, this experiment would have been impossible because we didn't have wide field cameras that had low enough readout noise to be able to do this, but they now exist. So what we can do is take all of the back end of a neutral atom quantum computer and then build that around an NV center setup. So none of the laser cooling, that stuff is too hard. But, an SLM, a low readout noise camera, and then use that to do massively multiplexed measurements on many NV centers in one field of view. So this is led by Kai-Hung Chang, who's a third-year grad student, rising third-year grad student in my group. So this is now, let me just play that again. This is a wide field image where we can do simultaneous ODMR of 200 something NV centers. What you should see is as I scan the microwave frequency, there are little things that go dark. And they go dark at different times because they have different orientations, right? Okay, so we can turn this into spectroscopy and do ODMR over this entire field of view very easily. We can translate this into a DC sensitivity map. We can do dynamics. So we can just measure all of these NV centers at the same time and do T1 measurements over, this total field of view is probably something like 40 microns by 40 microns. Okay, and then to do this covariance, the main kind of power-hungry thing is the spin to charge. So we can't just do everything in wide field. So what we have is a spatial light modulator for projecting a particular holographic pattern onto these NV centers. So we look in wide field, we find a bunch of NVs, we pick out the ones that we want to address, and we program that into the SLM. And then you can see that we've picked out specific NV centers with the SLM. And then we can use this to do simultaneous covariance among a bunch of NV centers. So this is not the hundreds that I promised, but we can do simultaneous covariance among 4. In this case, what we've done is intentionally flipped one NV center among 4. So you have a bunch of anti-correlations and a bunch of correlations. So these are the spin-spin correlations. And then we can do exactly the same XY8 noise sensing that I showed you earlier, where we see either an anti-correlation dip or a correlation peak as a function of frequency. The reason that we're stuck at 4 NV centers is that right now our readout noise is entirely determined by the total ionization power that we have. So as we start to split up the laser into more and more spots, then we pay a penalty in readout noise. And we can see that by the scaling with the number of multiplexed NV centers. Fortunately, this is an easy problem to solve because you just need like a really giant ionization laser. So we now have the scariest laser my lab has ever purchased coming next month to try to solve this problem. And we think that we can kind of easily get to tens of NV centers. Okay, the last piece, this is sort of a technical piece, but in order to actually do condensed matter sensing, you need to have some way of bringing the quantum sensors to the thing that you want to sense. And they need to be pretty tightly coupled because any offset is going to go into your spatial resolution. I think there's actually a big graveyard in this space where people try to do fabrication directly on the diamond. That is too hard. It's too hard because diamond is not that easy to work with. And also you've spent all this time making your nice quantum sensor substrate, and that has some finite probability. And then for those of you who do like transport and stuff, you probably do a lot of device post-selection. So that is not a 100% yield kind of process. So now you have a very bad p-squared problem because I need my quantum sensors to work out at the same time as my beautiful graphene device. So what we're doing instead is coming up with new diamond nanofabrication methods where we carve up the diamond. So this is monolithic diamond, but we do this very isotropic etching to undercut it. And we make these little membranes and frames of beams. The overlay here is a confocal scanning image that shows NV centers in these beams. We can then just pluck them out with a micromanipulator and then mechanically transfer them onto whatever we want. So if you have, all the device post-selection you wanted, this is a graphene device wired up in Ali Yazdani's group, then we basically pick the device and then slap our little diamond quantum sensor thing on top of it. And then we can image through that membrane. And then once you're going to all this trouble, you might as well do some photonics and try to get more photons out than those 100 kilocounts per second. Okay, that's all that I have. So the work that I talked about today was really led largely by Jared Rovney, who has been leading this covariance team for a few years now. The multiplexing work is led by Kai-Hung Cheng, and as I mentioned, this is all done in collaboration with Shimon Kolkowitz. There's a big group, big subgroup in the group that's working on covariance and condensed matter sensing. And then we now have, a large number of actual condensed matter physicist collaborators to try to apply this method to different materials. We've been talking a lot with Eugene Demler and Saranga Balakrishnan, have collaborations with Ali Yazdani, Leslie Shoup, and Abhi Pasupathy. And I'll stop there, and I'm happy to take any questions.
Me? I was wondering, especially when you bring your NV centers really close, do you ever observe correlated behavior, like correlated, not classical noise, but like correlated coherent noise? Both of the NV centers containing some photon or something. Is that very different than
like super units or something?
Not necessarily, but yeah.
We don't think so. So I mean, the conditions under which you would see like correlated TM, for example, are where you have pretty strong bipolar interactions. So in that case, then you just have like an entangled pair. But yeah, we haven't looked at that many. Are you asking from a condensed matter perspective? Like,
I'm looking because at least when I looked at the superconducting qubits, they're like effective spin-spin interaction is of the same order of magnitude
Oh, I
as the coherent noise between the two.
Yes. But there you have a pretty weird, so like a third of my group does superconducting qubits. So there you have like a pretty weird system because you're very strongly, you're in this ultra strong cavity QED coupling regime. So you can have a lot of weird correlations that just come through that itinerant photon, basically.
Yes, I have a question on how much control you have on the position of these NV centers. Can you take 20 of these NV centers and create a lattice?
Yeah, so, okay, so as I was saying earlier, we have a pretty good handle on depth because you just do ion implantation at some particular energy. So like, let's say we pick an energy where we expect the NV centers to be 5 nanometers from the surface. What we generally see to within a sigma is like 5 plus or minus 5 nanometers, roughly. We get a distribution from 3 to 10. So you can get a pretty thin layer. In terms of lateral positioning, you are entirely limited by like E-beam lithography. So, you could just make a mask and then cut holes in the mask and then ion implant through that mask. So you can get kind of accuracies of a few nanometers. But then, I don't know what kind of density you could make, but, it's just a question of what you want. For these very close NV centers, that's harder. It's not that easy to make a bunch of entangled pairs. But what we used is actually you could implant a nitrogen molecule instead of just a nitrogen atom or a nitrogen ion. And then that gives you a much higher probability of finding two that end up close together.
How many NV centers is involved in sample measurement, and how could this number affect the resolution and standard deviation? Also,
You're saying if I just use an ensemble instead of using single NV centers. Yeah, so you can kind of pick your ensemble. I think the typical density, the problem, okay, so here's the trade-off. So you want a lot of NV centers because then you just win by root n, right? Because you just get a lot of photons. Where you start to run into trouble is if you get to high enough densities, then you screw up your coherence time. Because not only do you have spin-spin interactions with the NVs, but actually our conversion efficiency to NV from N is not that good. So now you have all of these nitrogens that are also paramagnetic impurities that cause problems. So I think typically people are in a regime where they're looking at like hundreds of NV centers or something like 100 NV centers in a diffraction limited spot. That's kind of the rough sweet spot that most people work in. That's not fundamental. Like you could probably improve the material in different ways to do better than that. And then in terms of resolution, what that really means is that you're just stuck with the optical diffraction limit, right? Because if you're looking at this ensemble, now it's just how tightly can I focus my light? And you can do like stead and stuff like that, but then what are you winning? I'm not really sure. Like, I'm not sure if the overhead associated with that is actually worth it, but I don't know. I've said wrong things before, so maybe there's a reason to do it.
Also, could some mutual interaction between some fragile sample happens if you have a large enough ensemble of NV centers?
Yeah, if they're dense enough, then you can start to see ensemble interactions. And actually, there's a lot of very nice work. Sorry?
With a fragile sample.
With a
For example, let's say a fragile sample.
fragile sample.
Will there be any observable effects between the interaction between NV center and the sample?
Oh, you mean like back action or something?
Yes.
Oh, right. If you can get into a back action regime, then like, that's awesome. I think in general, no. I think generally your coupling to whatever it is that you're staring at is going to be very weak. So you're really just looking at classical fields.
Okay, I think due to limitation of time, we really need to move on to lunch. So let's thank Nathalie again for the talks.